Share the screen. Okay, we're going to go back to our code here. All right, so we were talking about the architecture, okay, of this model. So I'm going to switch to the whiteboard and kind of illustrate graphically what this is. Usually I'll do this, right? This is a good way of visualizing it. So we were talking about the iris data set and building an MLP, a multi-layer perceptron, and kind of this is the definition and the code. So I'm going to stop sharing and I'm going to switch to the whiteboard, new whiteboard, and use whiteboard classic. Okay. So now here, I'm going to think of what I'm doing, right? So this is the iris data set, which is X, okay? So this is going to be 150 by 4, right? So we've talked about this before. So essentially, we build a neural network with 4 nodes, right? That's going to be the input. So this is the input to the model, okay? Then we are going to have, because it's an MLP, we just really have one transformation. So this is going to be one hidden layer, hidden 1. And this could be like 6. I don't remember what the value is. If you guys can remind me. I think it was 6, right? And then finally, this is the iris data set. So we have an output layer, and that's going to be 3 classes. Okay? Does that make sense? So that's essentially what we're doing. So we're taking a model of 4 inputs, transforming each sample into 6, and then those 6 are transformed back into 3, the 3 labels, so that we can do the comparison. So that should be, this value is what I don't remember. I think it's 6 in the code. We'll see that in a second. Click on this. Okay, so we should be sharing now. So actually I did 3, not 6. I went, so it wasn't 6, it's 3. But essentially this is the way that you code that visual graphic. All right, so we've already talked about the definition here. So we essentially do the first linear and then linear from 4 to 3. So 3 is that I marked as 6 was actually 3. Okay, so I call that and then linear, or sorry, linear 1, so I can access it. Once that vector is produced, vector of 3, it goes into this function called a sigmoid, right? And the sigmoid just transforms all the values in it, okay? And we'll see that in a second. So that's going to be called an activation function. Activation functions are actually what makes these linear transformations into nonlinear transformations. So this is essential for really smart neural networks, actually. Okay, these activation functions. So there's many, tan, H, ReLU, GeLU, etc. But here's just an example of using sigmoid. Then after that, we would have another NN linear, which would be from that, what I marked as 6, right? That hidden layer 1 to the final layer that is 3, the output, right? Because we have 3 classes. And there, we've already spoken about the softmax. Here you can see I'm using a softmax for that last layer, essentially. Okay, so if we relate that back to the whiteboard, essentially here, I'll correct this, that this was not 6, it was actually 3. So I actually can erase this. So I made a layer of just 3 neurons. Okay, just like that. You can change it however you want. Play with it, see what works. There's no like theory about this. You should try different things. So once, remember that there's going to be a W here, right? W, let's call it 0. Matrix multiplication, the bias is it produces this vector. These vectors then are run through that function sigmoid. Okay. Sigmoid. And then you have yet another weight matrix here with that NN linear. So this vector times that plus the bias produces this vector. And these values have to run through the softmax. Remember? So these two activation functions, let's look at them. Essentially, we have sigmoid and softmax, right? And softmax. And sigmoid is usually something like this. Something like that, right? So it didn't come out perfect, but let me. It should be straight. Straight, and this is 1 usually. All right, so any values on the x on this axis to this axis, right? X to y. So the values from minus infinity to plus infinity become converted to values between 0 and 1. Do you guys see that? So that's essentially the higher the value is, the closer it gets to 1. The lower the value is, the closer it gets to 0. Okay? And that's what the sigmoid does. And then softmax, we've already established that when we want to create a probability distribution, right? Let's say we have 0.2, 0.5, 0.7, right? These values do not add up to 1. So what we apply a softmax here, and then the softmax then might do something like 0.10, 0.4, 0.5, something like that. You see that? And now the difference would be that this would add up to. Hey, this is an equation. It was in your 107 operation, so you should have seen it there, but it's, a simple operation. Any questions? All right, so that's what these functions do. Remember, softmax, very important for classification. We used it already in the GPT when we were out of the vocabulary, right? We wanted to predict the most likely term or token. So we used it there. Here, we're using it for the exact same reason. It should blow your mind, right? That something that we use for 3 labels here, we were also using it for a vocabulary of 50,000 or so words in the GPT. Same thing. And then the sigmoid is just one of the first activation functions you've seen. I think you've also seen a ReLU. Remember, a ReLU is the hockey stick. So the difference being with the ReLU that it's a hockey stick. So like that, right? So these are all 0, and then these are all just the value that it is, positive. Okay? All right, so we've talked about that. So now we can go back to just defining our architecture. Click on this. Okay, pretty simple. So I have, 4 to 3. It runs through a sigmoid, then 3 to 3 runs through a softmax, and I can use a dropout somewhere. I still haven't talked about dropout. I'll talk about it later, but it is a helpful thing. It just breaks connection. So think of a dropout as randomly. It's going to just take what percentage? 0.25% of the connections and just drop them like they don't exist. And so it trains with the other ones. You see that? So imagine that there's you're going from one city to another. And for whatever reason, there's like 1,000 highways. And they all like crisscross and zigzag between each other until you get to the city, right? So that would be pretty complicated to figure out which one's the best if you have to go through all of them. Do you see that? So what dropout does is 25% of those, like they don't exist, and then you go through the other ones. But every iteration, it drops a few randomly. And as it turns out, that provides good results to do that. You see that intuitively, I can tell you that it's maybe like trying different architectures and then arriving at the best one without you manually setting all these different architectures. It's like saying that I could have taken just the roads on the right side or just the roads on the left side, right? But the ones in the middle, then the ones in the diagonal like this. I could have chosen all of those things manually, or a more efficient approach is just to randomly pick them via dropout. Do you guys see that? So that's essentially, and that's an analogy with relation to the connections in the neural network. Okay, but anyway, that's dropout. A little more, Jeffrey Hinton, I think, invented this as well, and it works really well. All right, so as you can see, now we're in the neural network forward. So what do we have here? The X data comes in, right? X data comes in. What do we do to it? X minus X means. Remember, we might receive 120 by 4, and all of those during training are going to be, you're going to take each vector minus the mean. Got it? And that then is divided by the standard deviation. Okay? That's it. That's standardization. Once that's done, your X has been transformed from being on the normal scale to being on the standardized scale. It's been normalized or scale. Okay? Once this X is in there, then it goes to the first layer, the one of 4, gets transformed to 3, right? That vector of 3 then goes through the activation function, which is a sigmoid, to produce this value. You can apply a dropout here if you'd like. Then that goes to linear 2, which converts from 3 to 3, but being the last 3, the vector that is going to be the output. And then that vector is run through activation 2, which, if you remember, is the softmax. And that's it. Any questions about this, guys? All right, great. So it seems like it's pretty clear. Okay. So we've defined a whole architecture very easily. And that's called a multi-layer perceptron, usually traditionally, because it's got one input layer, only one hidden layer, one output layer. So effectively, you don't call this deep learning, right? Deep learning is when you have more than one layer in there. Okay. All right, so once we've defined this, which was already somewhat familiar to you, we go to the next step, and I'll do this deep DLNet later, right? So when we do the other architecture, but now we go to the training loop. And what might surprise you here is this is very similar to what we already did with the GPT. Exactly the same thing, almost, right? And so that's what I said before is that even though during that first third of the semester, every day everything was new, now you get to benefit from all of that because now it's repetitive in that sense because there's the only one approach. So here I have a function called training loop, provide the number of epochs, the model, which is going to be instantiating that class, loss FN, which we're going to be using cross entropy for this one that we need to define, and opt, which is the optimizer. Okay. Then I need to define these things in a second, but they are similar to what we did for the GPT. So now notice I have 2 for loops here, and this is how these for loops will be here. This is how I grab my data in batches. First of all, I'm going to repeat this process of grabbing my data set and a number of times defined by n epochs. I don't know if you guys understand that, but you really grab the whole data set, right? And the train set, and you give it to the model n times. So it's like I grab all of it, here it is, train. Grab all of it, here it is, train. Grab all of it, train. So if I say 6,000, right, for n epochs, it's going to look at the 120 samples 6,000 times. I don't know if for you guys this is clear, but I remember when I was learning about this, it's like, it seemed almost like cheating. I don't know why, but it just like, and this is one of those examples that shows you that machine learning is different, right? If humans, now humans we have a lot of context, right? But if a little kid is walking and they trip, it doesn't take them long to realize, hey, if I keep doing this, I'm going to trip. But here we're saying that little kid would have to trip 6,000 times. Do you see that? So it's a little bit different how they work, how neural networks work. But it may just be, nobody knows this, right? This is one of those things that's being researched currently. It may just be that humans just, even at 1 year old, we already have a lot of context about the world. And so that helps us so that we can learn faster. It's not clear. But anyway, this is one of those things. To me, as I honestly can tell you, I thought, okay, I should only give the data once. And this giving it the data 6,000 times is like cheating, it felt to me. But anyway, so you are literally giving it the same data set 6 times. So you can see now why shuffling the data every one of those times might be a good idea, might be useful, right? Because you're not always just giving it the same data, you're shuffling it in the process because you're learning in batches, right? So you're not giving all the data at once, you're giving 16 and another 16. So, but every iteration is a different set of those 16. And here in Iris, it really doesn't, it seems like it's trivial, but once you have a data set of 100,000 samples or so, then it makes more sense. Okay, so we have this. You can see I have this line here, squeeze, unsqueeze. This is usually sometimes the tensor that I'm grabbing doesn't quite fit. So this is usually where I would do something. I think here it's going to work just fine. But you can see the process is very similar to what I did in the GPT. From train DL, I grab XB and YB. We're able to do this because if you remember, they were tuples, right? So I'm grabbing a batch of the vectors of 4, and I'm grabbing the values, the integers, for that batch, okay, the corresponding ones. So XB has the X data, and YB has the labels that we are trying to predict. If you notice, these labels are literally 0, 1, or 3. They were integers. They're not vectors of 3. But I don't know if you notice that the neural network will produce vectors of 3. Do you see that? So you might think to yourself, okay, if I'm going to compare those two, shouldn't my labels be also vectors of 3? And in the past, that was the case. I mean, technically, like mathematically, that's the way it should be. But the thing that you're not like realizing is that the cross entropy function that we use understands that a lot of people will code this way. And so what it does is it's designed to take on one side a vector, let's say a vector of 3, and on the other one just the integer. And then it'll do the vectorization itself inside the function. Do you see that? So that's why we can get away with not doing this. But in the past, you actually have to do the one-hot encoding yourself. Okay. So anyway, if you notice X comes out and YB, then what do? I input XB into the model. What does the model do? It produces a prediction, right? A prediction, which should be a vector of 3. And then if you notice, that prediction is sent to this function called loss fn. So we send ypred, the prediction, along with the actual data, the actual label. Do you see that? So maybe it predicted a vector of 1, 0, 0, right? So that's saying that it's class 0. And then here, the class is 0. So in that case, what? You have a match. Do you see that? So that was a good prediction. That error is, there's no error, right? But it could be that it predicted 1, 0, 0, and the value here was 2. So that's a mismatch. Okay, and so that error needs to be, that's an error that is going to backpropagate to update the weights. And eventually, though, we hope that the predictions are going to be good. Got it? So don't worry about understanding cross entropy. I have a whole lecture for that in a Jupyter notebook for that. So we'll explore that possibly next week. So we are getting to the point where we're going to start to dig deep into these things. So cross entropy may actually be a topic, and we'll start with entropy that we cover next week. But not. I just have to see how I progress. I also have. Oh, we have a problem. What's the problem? Next week is actually full break. So you guys are going to fall behind again with the other class, right? So yeah, you catch up on Thanksgiving, right? So Thanksgiving, then they fall behind and it kind of, so, but this time you will fall behind from them. I have no alternative. So anyway, sorry, in 2 weeks, we'll look at cross entropy. All right, but it's coming up. It's in the notes. If you start reading all the material, you may not even need for me to explain it, right? Because you can also just, go through it yourself. All right. But anyway, as I was saying, so we give the XB to the model, it produces YPRED. YPRED gets compared to YB, right? And this is this function, we're defining loss Fn. We use a generic name usually, and then we define it later. There's really just two loss functions. Like this might surprise you also, right? So this process of training anything from Iris, the simplest thing, to GPT, the most complicated thing, at least in the pre-training stage, is actually the exact same process. And the functions are just two, MSE and cross entropy. There are no others. So stochastic gradient descent, there's only one. And then of the two losses, there's essentially just two. There's variants of them, but essentially there's just two. All right, so we'll see that later. All right, so we take the difference between the two of them. We already explained what this is, right? This is the node in the computational graph that connects everything. And then remember, I even asked a question on the exam about this. We have these 3 lines of code that are always there, right? And they are the ones that do all the heavy lifting, okay? So remember, opt 0 grad. Why do we do that? Because by default, PyTorch accumulates values, right? So we want to clear them out. And then after that, we do loss backward. What was that? The derivatives part. So that's also something that we will have some examples of how that actually works, the math of it. But here in the computational graph, it calculates the weights. Remember, the intuition is it a plus or a minus, right? From the value. And then finally, the step is when we do the update, okay? And that's it. This little line of code here just means that every 50 epochs, we're going to print what this loss value is. Remember, our goal with the loss is to what? For it to go down, okay? All right, so that's the function. And then we just need to instantiate a few things, and we should be able to run this one. All right, so the function is now set. Are there any questions with this function, guys? If this is key, right? So if you understand this in like the next 2-3 weeks, that's like the essence of this, plus a GPT. So it's like what I'm trying to say is like the most basic thing. If you miss something, then you might be confused later. But if you get those fundamental things, everything else should make sense. All right? All right, because this is the process that we will be repeating a lot. So I have the train loop function here. And now I just have to do this part here. And we can train the model. So here, if you notice, I'm going to take that class, MLPnet. X means X deviations that I calculated, right, before. I provide them. Our model is called, we usually call model. Then we instantiate the stochastic gradient descent algorithm. In this case, I could have used SGD, but I'm using this one called Atom. They're essentially the same as far as the math. It's just that the implementation, one is a little bit more efficient than the other. It's got like little tricks. Yeah, go ahead. Yeah, go ahead. It will be. I haven't defined it yet. So I only define MLP, which is the drawing that I did on. I will do it, yeah. But yeah, it'll have 2 or 3 layers. Mm-hmm. All right, so I define opt as torch.optim.atom. And remember that the nice thing that I really like about this is that we tie the model weights to the optimizer. And we do that by doing this. So model.parameters, actually, we'll see this a little bit later in the semester, is just the weights and the biases. Right, so as we could have coded the tensors independently, and we also plug in the learning rate, which is 0.03003, which is something that, it's the step, right? So how the increment, the increasing or decreasing is going to be based on this value. All right, and then after that, we have the function that is going to be assigned to loss Fn, which is cross entropy loss. Okay, and like I said, there's usually two of these. MSE or this one, and everything else is just variants of them. Okay, so rarely there's a situation where you need another one. Okay, and don't worry about this one. We'll discuss it in quite a lot of detail in the future. All right, and then once all of this is defined, we just plug it into our train function, and this function will start the training. So let's go ahead and do that. And I believe it's training. There it goes. So you can see in the 70s and the 60s and the 50s and the 50s. So it's kind of stuck in the 50s at this point. The X data is normalized, as you know, but it's kind of stuck there. Still good. Oh, it finished. Okay, so how many iterations? Was it 6,000? 4,000, I guess. All right, so yeah, it's done. So that means the model is trained now, and now comes the evaluation part. This is something we didn't do with GPTs, right? We didn't really evaluate them, although we can, there are ways. But here, this is definitely more intuitive. And whenever you're building these type of classification or regression models, you want to evaluate them. So we have a lecture on just what these metrics are. So that's going to be in the future. But for now, I'm just going to give you this function. I always just use this function, right? You don't have to reinvent the wheel. This function will provide all the metrics for a classification problem. There's a different one for regression. Essentially, we are going to create something called a confusion matrix. And from that confusion matrix, we extract precision, recall, and F1 measure. All right, and these parameters give you different insights into your results. Okay, so you're looking at things from the point of view of, think of it this way, out of the ones that I wanted, how many were correct? You see that? That might be different than how many did I get correct total. And so it's different ways of looking at the results. But we'll explore that in a future lecture. All right, and so now I have my function over here, and now I'm just going to evaluate performance by using this function. So a couple of things here. Here we want, whenever you do evaluation of your model, you want to do torch.nograd, because pytorch by default, every time that you run something that has gradients, like running the model, it updates the weights. Like it'll try to update the weights. But since we're evaluating here, we don't want to evaluate on the test set. Okay? Especially, let's say you were in a competition or something, you would not want the weights to be updated when they look at the test set, because that's cheating essentially. All right, so here we are. So with torch no grad, so that the updates are not made, we're essentially, another way of thinking about it is like we're freezing the weights. You see that? So the weights of the model cannot be updated at this moment. And then for X real, Y real, and test DL, you can see it's the same from the data loader. We run X real through the model. That gives Y pred. Then notice Y pred is going to be a vector, right? It's a vector of 3. So we want to extract from there the value, the index with the highest value, so we can use this function torch max. So torch max will provide the values and the indices, right? That are, so that in what we care about is the indices, right, which indicate the class, 0, 1, or 2. Does that make sense? Yeah. All right, so you extract that from the second dimension, and now we have those indices and preds, and we have the real values as well. And this is how we compare them. Okay, so out of the real, how many did we get right? Things like that in the prediction. So now I'm going to go ahead and run this, and there you are. This is how you analyze a classification problem. If we were doing a competition, which this year I won't do a competition in this class, but sometimes in the past I've done competitions where I've given you like everyone one data set, right? It's a much more complicated data set than this. And then you guys have to throw everything that you know about deep learning into that model to see who gets the best model, right? And how do I evaluate that model? By looking at this. Whoever has the highest values here would win. So for instance, here, the accuracy is 90%, precision is 90%, recall is 90%, F1 measure is 90%, right? And so somebody that gets a 95, that would be the winner. But yeah, these are the metrics that we have. As I said, we'll discuss these metrics in a future lecture. The confusion matrix is really nice because it compares predicted versus real for the three classes. Obviously, the goal is for the values to be only on the diagonal, right? And everything else should be 0. But because if we have values off diagonal, then that tells you that those are misclassifications. So it's handy because it tells you where something was misclassified, right? So it tells you that a value that should have been classified as a setosa is actually being classified as a virginica. And so it at least gives you some insight to figure out the problem. This should add up to 30, by the way, because there's 30 test samples. Any questions on this, guys? Does this make sense? All right, pretty easy, right? So this is and that's it. At this point, you have completed the classification pipeline. All right. What we're going to do now is we're just going to compare the other architecture, which is the DLNet, a deeper neural network. And we can build a deeper neural network here if we want. So I'm going to go ahead and go back up, or here actually. So this is the DLNet. So this is actually, I'm going to make this with 2 hidden layers. Yeah, oh, actually, it says it is 2 hidden layers. Huh? Oh, sorry. Let's actually make this fun. Let's give it like 4 hidden layers, right? So let's do 4 hidden layers just to see something, so you guys can think through it. But yeah, I think initially this is designed to have 2 hidden layers. All right. So now more hidden layers does not mean better results by default. I mean, but it could. It just depends. So obviously we have a performance and then around 0.90 across the board. We would want that to be better somehow. All right, so this one has the same thing. We're calling it class DLNet. It inherits NN module, as I said. And I wasn't kidding. This is going to become very repetitive, right? But that's great. You know, at least there's some consistency. We have your init function, x means, y deviations, the same. Super init is there. Then the forward function. We normalize the data and we have all these layers, right? So let's think about this now. You have a question? Yeah. So now, currently, the way that this is defined is 4, 15, 9, and 3. So let's go to the whiteboard. Okay. And so 4, 15, 9, and 3. So what does that look like? It should be 4. That's the input. 15. I'm not going to draw all of these. Dot, dot, dot. This is 15. 9. Dot, dot, dot. And then finally 3. So we can call this one hidden 1, hidden 2. Remember, there's a set of weights, W0, W1, W2, to make same thing we've been doing since the beginning, right? We take a matrix, the input data X, or the hidden layer, whatever it is, times that set of that weight tensor plus bias to produce the next one, and then H1, then H1 times W1 plus B1 to produce H2, then H2 times W2 plus B2 to produce the final output layer, or Y pred. Got it? Let's make this more fun, and let's create 4 layers. So I'm going to make 4 layers here. If you remember in the GPT, this was that feed-forward layer, right? Remember how we would go from 512 to 2048 and then 2048 back to 512? We were doing the exact same thing. Okay, so you can see the connections to the LLM. 1, 2, 3. This is 3. And this would be like hidden 1, hidden 2, hidden 3, hidden 4. And let's say this could be like 20, 15, 10, 5, and 3. How about that? Just so it's easy. Why those? Right? There's no real theory about this. When you have models, when this vector is really big, let's say like 784 or something, remember I said for images, you funnel it so every one becomes smaller, but this is so small that really you got to play with it a little bit. Okay, just don't make it too big. All right, so is this deep learning? Yes, this is what deep learning is. Deep learning is just more layers, right? Okay. There isn't a theorem out there that says that any neural network of this nature with an activation function is equivalent to that with sufficient number of neurons, N. Do you see what I'm saying? So like here I have 4 layers of 20, 15, 10, 5. There is an equivalent neural network of input, 1 hidden layer, output that is equivalent to this one as long as it has sufficient neurons here. Do you understand? So maybe you would argue 40 neurons here. Do you guys understand? The disadvantage with this problem, is now imagine this is the GPT. So the GPT had a lot of layers, right? So you would then say, okay, for this to be, the theorem says that there must be a neural network like this one, right? Which is just 1 input, 1 output, and a neuron on a hidden layer with sufficient neurons as the previous one. Well, in the GPT, this could be, right? You see my point. So what's the problem with that? Memory? It just becomes completely inefficient for many reasons. Do you see that? So although theoretically it might be possible, this is a preferred approach in terms of memory and such things. So this works better. Got it? All right. So let's go back to the neural net. So that one's going to be called a DL net. All right. So DL net, we're going to make it 4 layers. So you guys can tell me, right, what I need to do. I usually just like break things up just to be more, right? So I know I have 1 layer. So I know, so I have X means and X deviations, right? We've already established we want to do the normalization or standardization inside the architecture. We definitely know we need to have the first layer, right? So that's going to be from 4 to 20, right? So that's kind of how I defined it. Linear 1, and there's an activation function 1, ReLU, that hockey stick one. All right, what's the next layer then? How do I define these values now? See, this is the key now as you're defining the architecture, right? So on the exam, for instance, on the second exam, I could give you that picture and I tell you to write the code for this class. So how would you do it? 20, comma 15. Okay, good, right? And that's linear 2. Then let's save this one to be the last one because it already has the softmax in there. So then I'm just going to add another set of these, right? I'm going to name this one linear 3. This is going to be activation 3, the corresponding one. Everything else the same except these values. So what are these values now? 15, 9, 15, 10. 10. So 15, 10. Very good. Do you know why? Because it was in the, if I look at the graph, right? So let's go to the whiteboard. Remember 20, 15, 10, 5. So I'm changing it. That's what I said. You can use the one I provided, but just to make it more interesting, I decided to change it. Yeah, no, just change it. Yeah. All right. Yeah. So I'm doing this one. So now I'm gonna go back. All right, so we're here. All right, so I got linear 3 defined from 15 to 10. All right. What's the next one? Oh, I'm just going to copy these, right? So I'm going to copy these. I'm going to call them 4. Now, do we really need all these layers? No, it's probably overkill. But, to keep in mind, it will take longer to train too. But just as an example here. So what's this one then? 10 to 5? And then this was the last hidden layer, correct? So after this, we would go to the final output, right? Okay, so now we can use this one. Let's call it now 5. So this is linear 5, 5. Okay, we have a softmax. So what are the values here? 5, 3. Yes, very good. Do you see that, guys? That's it. How simple is that? And so that's essentially how you build these neural networks and play with them. So now we've defined them. Obviously, we need to do this sequence, right? So we know X comes in, it's going to be standardized inside the neural network, even in the Onyx model that we deploy on GitHub, it'll do it there because this is literally in the path. All right. These values are just going to get recorded, like they're constants in that Onyx file. All right, so what do? We got X then is normalized. Now it goes into linear 1, activation 1. Then it's, I have a dropout, so I'm just using that dropout throughout. So let's leave it. All right, that's the first one. Then the X goes into linear 2, then in activation 2 and a dropout. And then I just have to copy this for 3 and 4. So I'm going to copy this one. And then one more time. And I need to change these values, right? So you can see why I use this approach. Makes it a little bit more consistent. 3, right? And then this one is going to be 4, 4, right? And then at this point, 4 ends up being 5. So then 5 is the input to the last layer, right? And so it should connect easily. So this, we just have to make sure we're careful here to change this to be linear 5. And this activation 5 is the softmax. And that's it. So you've built your inference function. It's a very deep neural network of 4 hidden layers with ReLU activations, which essentially makes it definitely a deep neural network. Okay. All right, so any questions on this? Perfect. All right, so it seems like you guys are totally understanding this. So now I defined the class, and I'm going to go ahead now and instantiate it. The same thing, we're going to train now. Should it be better just because we made it deeper? Not necessarily, right? There's a lot of things that we have added. We added the dropout. Definitely the data is standardized. Let's see. But here we are. Now the data, I'm using the same data loaders, right? So it's the same test set. So I should be able to compare one to the other. So here I'm going to do the same. I'm going to take DLNet, takes in X means, X deviations to create a model, right? I instantiate opt. Notice that this model is now tied to opt. So the parameters are there. The loss function is still going to be cross entropy loss. And then I just invoke the function train loop, which we had discussed before. So I'm going to go ahead and run it. And there we go. So it's still getting stuck in the 50s, right? We would want this to go down to 4 or 3. Now, that being said, it still gets a 90 in the metrics, so that's still a pretty good model. Notice that this one seems to fluctuate a little bit more, right? 5, see 67 there, 67 again. Whereas the other one was a little bit more stable. So it could be that dropout. It is a deeper neural network, so it's got a lot more to train. Also, it's got way more capacity, but we gave it a lot more. 80, see you see an 80 there. We're almost done. So the losses are definitely something I would still say, although there's variation, you can see it went from 1.14 to 71. So in the first 100 iterations, it definitely went down. Then it kind of had trouble improving from there. But we can evaluate performance. So this is one way of making sure it's learning, but we also want to look at performance. So again, the same idea with torch no grad, because we always want to make sure that the model does not look at the test set, right? If or it is looking at the test set, but we don't want the weights to be updated in terms of that. That would be cheating. We give it we iterate through the test DL, the data loader, X real, Y real, plug in X real into model to produce Y pred. The same torch.max to select the indices with the highest values. And then in the print metrics function, we compare Y real to the preds, okay? So now let's see what it does, how it does. So what do you guys think? This is 0.933, so it is better. The other one was 0.90 across the board. Do you guys see that? It's a little bit better. Now the other DLNet, now this one, I was just playing with it. I looked at the Jupyter notebook here, and this one seems to have gotten even higher, right? So it might be that this is a good example where the architecture didn't need to be so complex. So instead of 4 hidden layers, I'm going to run this one with just 2. out of curiosity and see how it does. So I'm going to here at that one. This one, I'm not going to explain this one because you guys get it. But you know it's got a layer of 15, a layer of 9. We've got the dropouts in there. I'm going to call this one DLNet 2. All right. And let's just then do this again. All right, so this is DLNet 2. Normalizing. Model goes in here, cross entropy. Okay. So let's see how it does in this one. Still gets kind of stuck in that 0.55 range. All right, so it finished. So now let's evaluate performance again. All right, from test DL, Y X real, Y real, plug it into the model, produce Y pred, and then compare. Nope, 93. So maybe that 97 could be a result of just a different randomization of the data set. You see what I'm saying? When I did the split, so here, that's actually a really good point, right? So notice here I get a 93. In the previous one, I was getting 96.7. So it seems like one is much better than the other, but it could just be a result of the initial trained test split. So again, this is why it's a good idea to run this Jupyter 10 times or so. And every time that you run it, log this value. So that when you've done it 10 times, you'll have 10 of these values and then take the average. So if I was to report this now to you guys, I wouldn't be so confident as to say, let's say you're competing for $1,000, right? And you're going to enter, and obviously people are going to ask for your code and your results. They're going to assess it. So you shouldn't be so confident as to say my score is 97, right? Because really on another randomization, your score was actually 93. So if anything, you should say what? It is the average of those two, which is like, what, 95? And that's a more accurate description of your results. You see what I'm saying? So this is good practice always. Because you don't want to, you come in and show somebody 97 and they're really excited and then they see this 93. And some clients are very picky about things like that. All right. Any questions or thoughts? All right. So hopefully if you understood all of that, right, you've understood like the very basic pipeline of classification. At this point, you can I would argue you can now take any, you go to where you work and, they have like an Excel spreadsheet or something of data, and you can construct one of these, right? You can construct one of these and give them this analysis. And then later on, not today, I'll show you guys how to deploy these models, and then you could play with them. Okay. All right. So we've done classification, and I have the wine quality ones as well. So we do have 30 minutes left. So I'll start that today, especially because you guys are going to fall behind. let's get started with that. And you should be able on your own to play with it at home, right? And then I'll finish it up when we meet again in 2 weeks. So the idea with wine quality is going to be very repetitive. So some parts I'm not even going to explain anymore because, as I said, the beauty of this in a way is that at some point, you know most of it all the time. 80% of it is always the same code. But anyway, the goal with the wine quality is that I can use that data set for both regression and classification. So you get to see actually in the code the slight differences that transform a problem from regression to classification. All of this, by the way, is described in a lot of detail in the PDF and the blog post that I gave you. So make sure to read those, okay? Very important that you do that reading. All right, so I finished this one. So before I move on, are there any questions? All right, perfect. So I'm gonna close this one. I'm going to end this video here and start a new one. That way